Hi everyone, in today's video we are going to be talking about the Nusselt number. So for convective heat transfer over a flat plate with laminar flow, the Nusselt number in the x direction is equal to 0.332 multiplied by the Reynolds number in the x direction raised to the power of 1/2 multiplied by the Prandtl number raised to the power of 1/3. And our goal for this problem is going to be to maximize our heat transfer over a flat plate with uniform area. So let's draw out this plate. We have this large rectangular plate here, and there's this flow that is coming in from the left side, and that's hitting this surface right here. When these two interact, a boundary layer forms. So I'm going to draw it as such. And this boundary layer has some sort of length associated with it. And this plate also has some length associated with it, which is a change in our x direction. So I'm going to have this length as x. And once again, this surface over here is the one in which the flow is interacting with and forming this boundary layer. So as I said, the Nusselt number is a ratio of convective and conductive heat loss. So this is equal to the convective heat transfer divided by the conductive heat transfer. And we are very familiar with these terms so far. So the convective heat transfer coefficient we know is H, and our conductive heat transfer coefficient is modeled by K, our thermal diffusivity. And once again, we are talking about this all with this respect to this length in this x direction. So we must multiply this by x, our length of our plate. And this surface over here that I have drawn in pink is going to be the depth of this plate. So let's start expanding on our other terms, such as our Reynolds and our Prandtl number. So our Reynolds number, if you remember from Transport 1, is going to be the density multiplied by the velocity of a fluid multiplied by the length, and in this case is the x direction, so multiplied by x, divided by a viscosity mu. The Prandtl number is a ratio of momentum diffusivity and thermal diffusivity. So this is going to be momentum diffusivity divided by thermal diffusivity. And we've worked with thermal diffusivity quite a bit. Remember, that is our alpha term. And we said that alpha was equal to the thermal conductivity divided by the density multiplied by the heat capacity. So if we write that in over here, on the bottom, we're going to have a thermal conductivity divided by a density multiplied by the heat capacity. And momentum diffusivity, we talked about a little bit in homework 1, and that was the viscosity divided by the density. And if we divide these out, you'll see that this becomes the viscosity mu multiplied by the multiplied by the heat capacity C divided by our thermal conductivity K. So now we can plug in all of our values. So we had our Nusselt number was this Hx over K. Our Reynolds number was this rho Vx over mu. And our Prandtl number is this mu C over K. So we can plug that back into this equation up here. So our Nusselt number is our heat transfer coefficient multiplied by the length of our plate divided by thermal conductivity. This is equal to 0.332 multiplied by our Reynolds number in the x direction, which we said was the density times the velocity times x, our length, divided by our viscosity mu. This was to the power of 1/2. This is multiplied by our Prandtl number, which is the viscosity multiplied by the heat capacity divided by the thermal conductivity. This is to the power of 1/3. Now, looking at this equation, I notice that if I want to drastically change the heat transfer, I'm going to need to change this value here. And if we want to maximize our heat transfer, we want to maximize H, our heat transfer coefficient. So working this out, let's solve for H. So H is going to be equal to 0.332 multiplied by the Reynolds number, rho Vx, divided by mu to the 1/2, multiplied by mu c over k to the 1/3. And this is going to be multiplied by our thermal conductivity K divided by our length X, if we move our terms to the other side. Now we can see that in this equation, we have multiple Ks and multiple X's. So let's start expanding on our exponents. So over on the left, we have an X to the 1/2 power. This is multiplied by our term on the right, which is x to the -1 power. So if we multiply those, we add our exponents. So this becomes x to the -1/2 power. Looking at our k's, over on the left, we have k to the -1/3 power multiplied by, on the right, k to the 1st power. So if we multiply those and add our exponents, we get k to the power of 2/3. So let's put this back into our equation. So we have H, our heat transfer coefficient, is equal to 0.332 multiplied by rho to the power of 1/2 multiplied by the velocity to the power of 1/2 divided by our viscosity to the power of 1/2. This is multiplied by our viscosity to the power of 1/3, our heat capacity to the power of 1/3, multiplied by x to the power of -1/2 and k okay, k to the power of 2/3. Now looking at this, you'll notice that one thing that has a major impact on our heat transfer coefficient and our overall heat transfer is this length here. Because as you can see, if you were to increase this length of our plate or our x, we actually decrease our heat transfer because of that negative exponent. So looking up here, the larger that this x value is, the less heat transfer is going to occur. And once again, we want to maximize this heat transfer. So we want to minimize this x value right here. And in order to do that, we can orientate this plate so that the plate is perpendicular to the longer edge. Therefore, this depth that you see right here is increasing. So the amount of surface that this flow is hitting is increasing, and this length of this plate is decreasing. So once again, we decrease our length of our plate, we are going to increase the amount of heat transfer. So therefore, we can just simply orientate this to be perpendicular to the longer edge. Therefore, our heat transfer is maximized.